There is a quiet question that has followed us for as long as we have been able to think. A simple question that sounds small at first, but becomes deeper the longer you sit with it. And that question is this: how did life begin at all? And why is it still something we don't fully understand, even today? Even with all our science and technology, even after sending machines beyond our solar system and looking deep into space. Because when you really think about it, everything around you right now, every tree, every animal, every person, even you listening to this, all of it started from something that was not alive, and somehow, somewhere along the way, that changed. Something crossed a line that we still cannot clearly see, like trying to remember the exact moment. Night turns into morning. It happens slowly, quietly, almost invisibly, and yet it changes everything. So what exactly happened on Earth billions of years ago? How did lifeless matter become something that could grow, move, and eventually think? Because it's easy to assume we already know the answer. Many people believe scientists have already solved this mystery, that it's just hidden in complicated books or advanced research papers. But the truth is much simpler and much more surprising. We don't fully know. Not yet. And that's what makes it so fascinating, because usually, when we study something in science, we can test it, repeat it, watch it happen again. But the origin of life is different. It only happened once. Or at least we have only seen it happen once, right here on Earth. And that makes it incredibly hard to study, like trying to figure out how a single drop of ink spread across an entire ocean after it has already mixed completely. You can see the result, but tracing it back to the very beginning is almost impossible. And when scientists try to recreate the origin of life in labs, they can make some of the basic building blocks, simple molecules that are kind of like tiny pieces of a much larger puzzle, but turning those pieces into something that is actually alive, something that can copy itself and evolve. That's where things become much more difficult, because life is not just about having the right ingredients, it's also about how those ingredients come together in just the right way, at just the right time, like trying to build a working clock by randomly shaking a box full of gears and springs. It's not impossible, but the chances feel incredibly small. So this leads to a natural question. If it's so difficult for life to start, why does it exist at all? Why did it happen here, on this one planet, and nowhere else that we can clearly see? Or is that even true? Could it be that life didn't actually begin here, that it came from somewhere else, carried across the vast emptiness of space, like a tiny hidden passenger? Because when you look at the universe, it is unimaginably large, so large that even light, which travels faster than anything we know, takes billions of years to cross it. If you could drive a car at highway speed without ever stopping, it would take longer than the entire history of human civilization just to circle our own planet, once compared to crossing even a tiny fraction of space. So in a place that vast, is it really reasonable to think life only started once, in one small corner? Or could it be more common than we imagine, quietly forming in places we haven't looked yet, or even traveling between worlds without us noticing? And this is where the mystery becomes even more interesting, because instead of asking how life began on Earth, we begin to ask a different question. What if life didn't begin on Earth at all? What if the story of life here is not the beginning, but just one chapter in a much larger story, a story that started long before our planet even existed, drifting through space, waiting for the right place to grow? And as strange as that might sound at first, it's not just science fiction. It's an idea that scientists have seriously considered, an idea that slowly begins to change how we think about life itself. Because if life can exist beyond Earth, even in the smallest form, then the universe may not be as empty as it seems. It may be quietly alive in ways we are only beginning to understand. As we move forward, feel free to share where you're listening from, or leave a quick thought below. And if this channel means something to you, subscribing is a small way to support the journey. When we begin to look closer at the timeline of Earth's history, something surprising starts to stand out. Something that feels almost too quick to be real, because our planet formed around 4.5 billion years ago, which is such a large number that it's hard to truly picture. It's like stacking one year on top of another until the pile reaches far beyond the height of the tallest mountains on Earth. And yet, not long after that, maybe within just a few 100 million years, there are signs that life was already here, quietly existing. And if you think about that in a simpler way, it's like building a brand new house and finding that plants have already started growing. Inside it, almost immediately after the walls are finished, it feels fast, almost suspiciously fast, so fast that it makes scientists pause and ask, did life really start that quickly on its own, or was something else involved? Because in the early days of Earth, conditions were only just beginning to settle down enough for life to exist at all. The surface was still cooling, oceans were forming, and the environment was changing constantly. So the fact that life seems to appear so soon after all of that raises an interesting possibility. Maybe the process of life beginning is not as slow as we once thought. Or maybe, and this is where things become more intriguing, life didn't actually start here during that short window of time. Maybe it arrived already prepared, like seeds carried by the wind that begin to grow the moment they touch the ground. And this idea naturally leads to another question. How do we even know when life first appeared? How can we look that far back in time? And the answer lies in tiny clues left behind in rocks, ancient rocks that have been around for billions of years. These rocks contain small patterns and chemical traces that suggest life was once present, almost like footprints, frozen in time. And while they are not perfect records, they give us a rough idea, like trying to guess when someone entered a room based on the warmth they left behind. And what these clues seem to show is that life appeared very early, possibly as soon as the planet became stable enough to support it, which again feels incredibly fast when you consider how complex life eventually becomes. Because even the simplest forms of life today are still extremely detailed on a microscopic level, more complex than any machine humans have ever built, and yet they seem to have appeared almost as soon as the stage was set. So does that mean life forms easily, like water freezing into ice when the temperature drops, or does it mean something else entirely? Because many people assume that given enough time, life will naturally appear anywhere. But that may not be completely true. The process might actually be very rare, like winning a lottery where the odds are almost impossible to imagine. And if that's the case, then the speed at which life appeared on Earth becomes even more puzzling. It would be like someone winning that impossible lottery on their very first try, and that doesn't quite sit comfortably with what we know about chance and probability. So we are left with a quiet but powerful question. Was Earth just incredibly lucky? Or was life already out there, waiting for a place like Earth to arrive? And when you think about how vast space is, filled with countless planets and stars, it starts to feel less unlikely that life could have existed somewhere else before Earth even formed. Because if even one place in the universe managed to create life earlier, then over millions or even billions of years, tiny forms of that life could have traveled slowly, silently, carried by rocks, dust, or ice, moving across space in ways that seem almost impossible, but not entirely. And when they finally reached a young planet like Earth, ready and waiting, they could begin to grow almost immediately, making it seem as if life appeared quickly here, when in reality, its story may have started much earlier and much farther away. And this idea doesn't just change how we see Earth, it changes how we see ourselves. Because instead of being the very beginning, we might simply be part of something that has been unfolding for a very long time, something that stretches across distances so large that even imagining them feels like trying to count every grain of sand on every beach in the world, and still coming up short. So the speed at which life appeared on Earth is not just a detail in history, it's a clue, a small hint that there may be more to the story than we once believed, a quiet suggestion that life in its simplest form might not need to start from nothing every single time. It might just need the right place to begin again. If you could travel back to the very early days of Earth, you might expect to see something calm and peaceful, maybe vast oceans under a quiet sky. But the reality would be very different, almost unrecognizable compared to the world we know today. Because early Earth was a violent and chaotic place, more like a constant storm than a stable home, with massive volcanoes erupting across the surface, pouring out rivers of glowing lava that stretched for miles, like entire landscapes melting and reshaping themselves over and over again, the air thick with gases that would be impossible to breathe. And above it all, the sky filled with incoming rocks from space, crashing down with enormous force, like an endless rain of fire and stone, each impact releasing energy so powerful it could flatten entire regions, similar to thousands of nuclear explosions happening again and again. So when we imagine life beginning in such an environment, it naturally raises a question: how could anything survive in a place like that, let alone begin there? Because when we think of life, we usually picture calm conditions, stable environments, something gentle enough to allow fragile beginnings to grow. But early Earth offered almost the opposite. It was unpredictable, constantly changing, and often destructive. And yet, somehow life still appeared, which makes the situation feel almost like trying to light a candle in the middle of a hurricane. It doesn't seem impossible, but it does seem incredibly difficult. So this leads to wonder if maybe life didn't start during the worst of this chaos. Maybe it waited until things settled down, until the surface cooled and the constant bombardment slowed. And that's partly true. There was a time known as the Late Heavy Bombardment, when impacts were especially intense. But even after that period, Earth was still far from peaceful. Volcanoes remained active, the atmosphere was still very different, and the oceans, while present, were not as stable as they are today. So the idea that life formed completely from scratch in such conditions becomes harder to imagine, because not only would the building blocks of life need to form, they would also need to survive long enough to come together in the right way, and then continue to exist without being destroyed by the next major event, which could happen at any moment, like trying to build a delicate sand structure, while waves keep crashing over it again and again. So how did anything manage to last long enough to become alive? And this is where some scientists begin to think differently. Instead of imagining life forming entirely on the surface, exposed to all this chaos, they consider the possibility that it may have started in more protected environments. Places like deep underwater near hydrothermal vents, where heat and chemicals rise from beneath the ocean floor, creating pockets of relative stability, almost like hidden shelters in the middle of a storm. And in these environments, conditions might have been just right for simple molecules to come together, shielded from the worst of the impacts and radiation above. But even then, the process is far from simple, because life requires not just the right conditions, but also a sequence of events that align in a very specific way. And the more we learn about this, the more we realize how delicate that balance might be. Which brings us back to the bigger question: if early Earth was so hostile, does it make more sense that life began here anyway? Or could it have arrived from somewhere that was more stable, somewhere that had more time and fewer disruptions? Because when we look beyond Earth, we find that there were other places in our solar system that may have once had calmer conditions, places like ancient Mars, which might have had liquid water, and a more stable surface before Earth fully settled. So it's possible that life could have begun there first, in a quieter environment, and then later made its way here, carried by rocks, thrown into space by impacts, eventually landing on Earth and continuing its journey. And while this idea might sound unusual, it actually helps answer some of the questions raised by Earth's early hostility. Because instead of life needing to survive constant destruction while forming, it could have developed somewhere more suitable, then arrived here already prepared to endure, like a traveler moving from one place to another, bringing with it everything needed to start again. And this way of thinking changes how we view those violent early days, because instead of being the birthplace of life, Earth might have been more like a testing ground, a place where life proved it could survive even under extreme conditions, adapting and evolving through challenges that would have seemed impossible at the start. And over time, as the planet slowly became more stable, life was able to spread, grow, and eventually transform the world into the one we recognize today. So while early Earth may have been harsh and unforgiving, it also may have played a crucial role, not necessarily as the origin of life, but as the place where life learned to endure. And that idea opens the door to a much larger story, one that reaches far beyond our planet, into the wider universe where similar conditions might exist, waiting quietly for life to arrive and begin again. When we imagine life beginning from nothing, it often sounds simple at first, almost like a natural step, as if you just gather the right ingredients and wait long enough, and eventually something alive appears. But when scientists take a closer look at what that actually means, the process becomes much more complex, almost surprisingly so, because life is not just a random mix of chemicals. It is a highly organized system, where every tiny part has a role, and everything works together in a very specific way, like a perfectly built machine made of pieces so small you can't even see them. And this raises a quiet but important question. How do you go from simple, lifeless molecules to something that can grow, copy itself, and respond to its environment? Because that jump is not small. It's enormous, like going from a pile of loose bricks to a fully built city, complete with roads, buildings, and systems that keep everything running. And the challenge is not just building something complex, but building something that can keep going on its own, something that can make copies of itself and pass on information, because that's one of the key features of life, the ability to replicate, to continue, to evolve over time. And when scientists try to recreate this process in laboratories, they can often produce some of the basic parts, simple organic molecules that are like the letters of an alphabet, but turning those letters into meaningful sentences, and then into entire stories. That's where things become much harder, because it's not just about having the right pieces. It's about arranging them in a way that works, and doing it under conditions that allow that arrangement to stay stable, long enough to develop further. And this leads to another natural question. Could this have happened randomly, just by chance, over a long enough time? And many people assume the answer is yes, because given billions of years, almost anything seems possible. But the reality is a bit more complicated, because while time increases the chances, it doesn't guarantee the outcome, especially when the number of possible combinations is so large that it's almost impossible to imagine, like trying to guess a specific grain of sand out of all the beaches on Earth on your very first try. The odds are not just low, they are incredibly low, and yet, life did appear, which suggests that either the process is not as random as it seems, or there were conditions that made it much more likely, or perhaps, and this is where the idea becomes more interesting, life didn't start completely from scratch, on Earth at all. Maybe some of the more difficult steps had already happened somewhere else, somewhere with more time or more stable conditions, and what arrived on Earth was not just simple chemicals, but something closer to life already, something that only needed the right environment to begin growing and evolving, like planting a seed, instead of trying to create the entire plant from raw materials. And this idea helps address one of the biggest challenges in understanding the origin of life, because it removes some of the most difficult steps from the equation, steps that scientists still struggle to explain fully, and places them somewhere else in the universe, where different conditions might have made them easier. And when you think about how vast the universe is, with countless planets and environments, it becomes less unreasonable to imagine that somewhere, at some point, those steps could have happened. And once they did, the results could travel, slowly but surely, carried by natural processes we are only beginning to understand. And this way of thinking doesn't solve the mystery completely. It simply moves the starting point, pushing the question further back. Because even if life didn't start on Earth, it still had to start somewhere, and that brings us back to the same fundamental mystery, just on a larger scale. But it also changes how we view our planet, because instead of being the place where life began from nothing, Earth might be one of many places where life continued, where it found a home and began to grow into the incredible diversity we see today. And this perspective makes the universe feel a little less empty, a little more connected, as if life is not something that appears in isolation, but something that can move, spread, and take root wherever the conditions allow. And while we may not yet have all the answers, the difficulty of starting life from scratch reminds us that this story is far from simple, and that the origins of life may be part of a much larger journey than we once imagined, a journey that stretches across space and time, quietly unfolding in ways we are only beginning to explore. As we slowly move deeper into this mystery, a new idea begins to take shape, one that feels both simple and almost unbelievable at the same time. And that idea is called Panspermia, a word that might sound unfamiliar at first, but its meaning is actually quite easy to understand. It suggests that life did not begin on Earth, but instead came from somewhere else in space, carried here in tiny forms that were already alive, or close to becoming alive, like seeds drifting through the air until they land on the right patch of soil, and once they do, they begin to grow. So what exactly does this idea propose, and how could something like life travel across the emptiness of space? Because when we think of space, we often imagine it as completely empty, a vast black void with nothing moving through it. But that's not entirely true. Space is filled with dust, ice, and rocks of all sizes, from grains smaller than sand to massive objects as large as mountains. And these objects are constantly moving, sometimes slowly, sometimes at speeds faster than anything we experience on Earth. And every now and then, some of these rocks enter a planet's atmosphere and land on its surface. These are what we call meteorites, and they arrive more often than most people realize, like a quiet rain that never fully stops. So the idea behind Panspermia is that some of these rocks could carry microscopic life, hidden deep inside them, protected from the harsh conditions of space. And when they land on a planet with the right environment, that life could begin to grow and spread. And this naturally leads to a question: is that even possible? Could something alive really survive such a journey? Because space is extremely cold, far colder than the coldest places on Earth, like being placed in a freezer that is so powerful it makes Antarctica feel warm by comparison. And it is also filled with radiation, invisible energy that can damage living cells. So at first, it seems unlikely that anything could survive. But when scientists study certain types of microorganisms, they find something surprising. Some of them are incredibly resilient, able to survive conditions that would normally destroy life. And this discovery begins to make the idea of panspermia feel a little less impossible, because if life can endure extreme environments here on Earth, maybe it can endure the journey through space as well. And there are actually different versions of this idea. Some suggest that life could travel between planets within the same solar system, for example from Mars to Earth, while others imagine it moving between star systems carried over distances so large that even light takes years to cross them. And while that second idea is much more difficult to imagine, it's not completely ruled out, especially when we consider how long the universe has existed, billions upon billions of years, which is like having an endless amount of time for even the rarest events to occur. So why do scientists take this idea seriously? Is there any real evidence? Or is it just speculation? And the answer is somewhere in between. We don't have direct proof that life has traveled through space and landed on Earth, but we do have clues that make the idea worth exploring. For example, we have found organic molecules, the basic building blocks of life, in meteorites that have landed on Earth, which shows that some of the ingredients needed for life can form in space and survive the journey here. And this alone is a powerful hint, because it tells us that space is not completely empty of life-related material. It's actually filled with it, scattered across vast distances, waiting to come together under the right conditions. And this leads to another interesting thought. If the ingredients for life are already out there, and if they can travel between worlds, then maybe life itself is not something rare and isolated, but something that can spread, slowly but steadily, across the universe, like a quiet chain reaction that connects distant places in ways we are only beginning to understand. And when you think about it like that, Panspermia stops feeling like a strange idea and starts to feel like a natural extension of what we already know. Because if seeds can travel across a forest, carried by wind or animals, and grow wherever they land, then perhaps life can do something similar on a much larger scale, moving across space instead of land, carried by rocks instead of air. And while we still have many questions, the idea of panspermia offers a new way of looking at the origin of life, not as a single event that happened once in one place, but as part of a much bigger story, one that might still be unfolding right now, quietly beyond our view, as life continues its journey through the universe, waiting for the next place to begin again. Long before we had modern technology, before telescopes could clearly see distant planets, or spacecraft could travel beyond Earth, there were already people quietly thinking about the possibility that life might not have started here. And this idea did not suddenly appear in recent times. It has roots that go back much further, to thinkers who simply looked at the world and asked questions that others had not yet considered. Because even in ancient times, people wondered about the origin of life, and some of them imagined that it might have come from the sky, carried down in ways they could not fully explain, like rain falling from clouds that seemed mysterious and unreachable. And while these early ideas were not based on experiments or scientific data, they show something important. The curiosity about life's origin has always been there, quietly growing through generations. And as time moved forward and science began to develop, this curiosity started to take a more structured form, turning into real theories that scientists could discuss and explore. And one of the earliest figures to speak about something similar to panspermia was a Greek philosopher named Anaxagoras, who lived more than 2,000 years ago. And he suggested that life might exist throughout the universe, carried in tiny particles that spread from place to place, almost like invisible seeds scattered across space. And even though he did not have the tools to test this idea, it shows how long this thought has been part of human thinking. And later on, as science continued to grow, more scientists began to revisit this concept, looking at it not just as a philosophical idea, but as something that might actually be possible. And one of the most well-known scientists to support this idea was Svante Arrhenius, a Swedish scientist who lived in the early 1900s. And he proposed that tiny forms of life, like spores could be pushed through space by radiation from stars, almost like leaves being carried by a strong wind. And while this might sound unusual, it was one of the first attempts to explain how life could actually travel between worlds using known physical forces. And this raises a natural question: could something so small really survive such a journey? Because even if radiation can push particles through space, that same radiation can also damage living cells. So how could life endure that process? And this is where the idea becomes more complex. Because while Arrhenius's version of panspermia was creative, later scientists began to question whether it would actually work in reality. Since space is not just empty, it is filled with challenges that make survival very difficult. But instead of abandoning the idea completely, they started to adjust it, refining it into forms that might be more realistic. And this is how panspermia slowly evolved over time, from a simple philosophical thought into a more detailed scientific discussion, shaped by new discoveries and a better understanding of space. And another important moment came when scientists began to realize that rocks could travel between planets, especially after large impacts, which can send debris flying into space. And some of that debris can eventually land on other worlds. And this provided a much more practical way for life to move. Because instead of being exposed directly to radiation and vacuum, microorganisms could be protected inside rocks, shielded from the harsh environment outside, almost like passengers inside a natural spacecraft. And this idea gained more attention as we started to study meteorites more closely, finding that some of them contain complex organic molecules, which suggests that space is not just empty, but filled with the building blocks of life. And over time, more scientists began to take panspermia seriously, not as a proven fact, but as a possibility worth exploring, because it helps answer some of the difficult questions about how life could begin so quickly and under such harsh conditions on early Earth. And today, the idea continues to be studied, discussed, and tested in different ways, with experiments that examine how microorganisms respond to space-like conditions, and missions that look for signs of life or organic material beyond Earth. And while we still do not have direct proof that life came from space, the fact that this idea has been considered for so long, across different cultures and periods of history, shows that it is not just a random thought. It is a natural question that arises when we try to understand our place in the universe. Because when you look up at the night sky and see countless stars stretching in every direction, it becomes harder to believe that life would only exist here, on one small planet, and nowhere else. And so the idea of panspermia continues to quietly remain, not as a final answer, but as a possibility that connects us to something much larger, a reminder that the story of life may not begin and end on Earth, but may extend far beyond it, carried across space by processes that have been unfolding for longer than we can truly imagine, like a slow and endless journey that started long before we were here to ask these questions, and may continue long after, moving from one world to another, quietly shaping the universe in ways we are only beginning to understand. If you step outside on a clear night and look up at the sky, it may seem calm and still, but in reality, Earth is constantly being visited by small pieces of space, tiny fragments of rock and metal that travel across vast distances before finally reaching our planet. And these visitors arrive more often than most people realize, not just once in a while, but almost every single day, like a gentle but invisible rain that rarely gets noticed. And while many of these pieces burn up as they pass through the atmosphere, creating brief streaks of light that we call shooting stars, some of them survive the journey and land on the ground, becoming what we know as meteorites. And these meteorites vary in size. Some are as small as grains of sand, while others can be as large as a car, or even bigger, like a massive boulder falling from the sky. And this leads to an interesting question. If rocks from space are constantly landing on Earth, could they be carrying something more than just minerals and metal? Could they be carrying life, or at least the ingredients needed for life? Because when scientists began to study meteorites more closely, they discovered something surprising. Many of these rocks contain organic molecules, the same kinds of molecules that are involved in the chemistry of life. And this discovery changed the way we think about space, because it showed that the building blocks of life are not limited to Earth. They exist beyond our planet, scattered across the solar system, and possibly far beyond, like pieces of a puzzle spread out over an enormous area, waiting to come together in the right place. And this naturally leads to another question. How do these meteorites travel in the first place? How do they move from one world to another? And the answer often begins with powerful impacts. When large objects collide with planets or moons, they can send fragments of rock flying into space at incredible speeds, like debris thrown outward from an explosion, and some of these fragments escape the gravity of their original world and begin drifting through space, sometimes for millions of years, before eventually being pulled toward another planet. And if you imagine this process, it's almost like pieces of one world being scattered and then slowly collected by another, creating a kind of exchange that happens over very long periods of time. And this idea becomes even more interesting when we consider that some meteorites found on Earth have been traced back to specific places, including Mars, which means that material from one planet can indeed travel to another. And this raises a quiet but powerful possibility. If rocks can make that journey, could life make it too, hidden safely inside those rocks, protected from the harsh conditions of space? Because while the surface of a meteorite is exposed to extreme heat when it enters Earth's atmosphere, the inside can remain relatively cool, like the center of a loaf of bread, staying soft even when the outside becomes crusty in an oven. And this means that anything deep inside the rock could potentially survive the journey, shielded from both the heat of entry and the radiation of space. And this leads us to wonder about the scale of this process. How often does this happen? And the answer is more often than you might think. Over billions of years, countless meteorites have landed on Earth, bringing with them materials from different parts of the solar system, like a slow but steady delivery system that never really stops. And when you think about that over such a long time, it becomes easier to imagine how even rare events could eventually occur, because given enough time, even unlikely things can happen, like flipping a coin and getting heads again and again, until eventually it lands on tails. It may take many tries, but it does happen. And so the idea that meteorites could carry life, or its building blocks, becomes less far-fetched when you consider the sheer number of opportunities for it to occur. And this also changes how we view Earth, because instead of being completely isolated, our planet may be part of a larger network, exchanging material with other worlds over long periods of time, like distant islands connected by invisible currents. And while we still do not have direct evidence that living organisms have been delivered to Earth in this way, the presence of organic molecules in meteorites shows that at least some parts of life's chemistry can survive the journey. And that alone is a significant clue, because it suggests that space is not just empty and lifeless, but filled with potential, filled with the raw materials needed to build something more complex. And this idea gently shifts our perspective, making us realize that the boundary between Earth and space is not as strict as it might seem, because over time, pieces of space have become part of Earth, and pieces of Earth may have traveled outward as well, creating a quiet exchange that has been happening for billions of years. And within that exchange, there may be a story we are only beginning to uncover, a story where life is not confined to one place, but can move, adapt, and perhaps even spread, carried inside simple rocks that drift through the darkness until they find a new world to call home. As scientists continued to study the meteorites that land on Earth, they began to notice something that quietly changed the way we think about space. Something small but incredibly important, because inside some of these ancient rocks, they found organic molecules, the same types of molecules that are involved in the chemistry of life. And at first, this might not sound like a big discovery, but when you take a moment to think about it, it becomes something much more meaningful, because these molecules were not formed on Earth. They were formed somewhere out there in space, long before they ever reached our planet. And that leads to a simple but powerful question. If the basic ingredients for life exist beyond Earth, how common might they actually be? Because organic molecules, like amino acids, are often described as the building blocks of life, similar to how letters are the building blocks of words, and words are the building blocks of entire books. So finding these molecules in space is like discovering that the alphabet itself is scattered across the universe, waiting to be arranged into something more complex. And this discovery becomes even more interesting when we realize that these molecules have been found not just in meteorite, but also in distant clouds of gas and dust, between stars, regions so vast that they stretch across distances that would take light years to cross, which is like traveling at the speed of light, faster than anything we can imagine, and still taking years just to go from one side to the other. And within these enormous regions, scientists have detected complex molecules floating freely, forming and interacting in ways that suggest chemistry is happening everywhere, even in the cold emptiness of space. And this naturally leads to another question. How do these molecules form in such extreme conditions? Because space is incredibly cold, often hundreds of degrees below freezing, far colder than any winter on Earth, like placing something inside a freezer that never turns off and continues getting colder. And yet, even in these conditions, chemical reactions can still occur, especially on the surfaces of tiny dust particles, where atoms can meet, combine, and slowly build more complex structures over time. Almost like frost forming delicate patterns on a window, except instead of ice crystals, it's molecules slowly coming together. And this process can take a very long time. But in space, time is not a limitation. There are billions of years available for these reactions to happen, which is like having an endless amount of time to slowly assemble something piece by piece, without any rush. And over that time, simple molecules can gradually become more complex, leading to the formation of substances that are closely related to those found in living organisms. And this challenges a common belief that life's chemistry is unique to Earth, because many people assume that the molecules needed for life only form under special conditions found on our planet. But the evidence suggests otherwise. It shows that these molecules can form in many different environments, even far from any planet, which means that the ingredients for life might be much more widespread than we once thought. And this brings us back to the idea of panspermia, because if space is already filled with these building blocks, then the process of life beginning might not require starting from nothing every single time. Instead, it could begin with materials that are already partially assembled, like starting a puzzle with many of the pieces already connected, making the final steps easier to complete. And this idea also helps explain how life could appear relatively quickly on a young planet, because if some of the necessary components are already present, delivered by meteorites, or formed in space, and then brought to the surface, then the planet does not need to create everything from scratch. It only needs to provide the right conditions for those components to come together and continue developing. And when you think about this on a larger scale, it paints a picture of a universe that is not empty and lifeless, but one that is quietly filled with the potential for life, where the basic ingredients are spread across vast distances, waiting for the right environment to bring them together. And this perspective changes how we see our place in the universe, because instead of being a unique and isolated event, life on Earth might be part of a much bigger pattern, one that repeats itself in different places, guided by the same basic chemistry that exists everywhere. And while we still do not know exactly how these molecules turned into living systems, the fact that they exist beyond our planet is a strong reminder that the story of life may begin long before it reaches a world like Earth, starting quietly in the cold depths of space, where simple atoms slowly come together, forming the foundation for something much more complex, something that, under the right conditions, can eventually become alive. When you begin to connect all these small discoveries together, a quiet realization starts to form, almost like watching scattered pieces slowly come together into a clear picture. And that realization is this: the building blocks of life are not rare. They are not limited to one place. They are everywhere, spread across space in ways that are easy to overlook, but hard to ignore once you see them. Because we have now found organic molecules in meteorites, in comets, and even in the vast clouds between stars, and each of these discoveries adds another piece to the same idea, that the universe is filled with the raw materials needed for life, almost like a kitchen where all the ingredients are already laid out, waiting for someone to begin cooking. And this leads to a simple but powerful question. If the ingredients are everywhere, does that mean life itself is also common? Or is there still something special that needs to happen, something rare that turns these basic parts into something alive? Because having ingredients alone is not enough. Just like having flour, sugar, and eggs does not automatically create a cake. They need to be combined in the right way, under the right conditions, and at the right time. And that step, the step where non-living matter becomes living, is still one of the biggest mysteries we face. But knowing that the ingredients are so widespread changes the way we think about that mystery. Because instead of asking how those ingredients formed, we now focus more on how they come together and where they might do so. And when you look at the universe, there are countless places where this could happen. Planets with oceans, moons with hidden water beneath their surfaces, and environments we have not even discovered yet, each one offering a different set of conditions that could allow these building blocks to interact and evolve. And when you think about the scale of it all, it becomes almost overwhelming, because there are more stars in the observable universe than there are grains of sand on all the beaches on Earth combined, which is like trying to count every grain of sand you can imagine, and then realizing you still haven't even come close. And around many of these stars are planets, each one a potential location where the ingredients of life could gather and begin something new. So the idea that life's building blocks are everywhere makes the universe feel less empty, less silent, as if it is quietly filled with possibility, waiting for the right conditions to bring something to life. And this also challenges another common belief, that life is something extremely rare, something that only happened once, here on Earth. But if the ingredients are so common, then maybe life is not as rare as we think. Maybe it is just difficult to detect, hidden in forms that are small, simple, or far away, beyond our current ability to observe. And this leads to another question. If life can form in many places, why haven't we found clear evidence of it yet? And the answer may be that we are still in the early stages of searching, like standing at the edge of a vast ocean and only looking at a small patch of water. We cannot expect to find everything right away, especially when the distances involved are so enormous, and our tools, while advanced, are still limited compared to the scale of what we are trying to explore. But even with these limitations, the discoveries we have made so far are enough to suggest that the universe is not a lifeless void. It is a place where the chemistry of life is happening all the time, quietly and continuously. And this idea also connects back to Panspermia, because if the building blocks of life are everywhere, then the process of spreading life becomes more plausible. since these building blocks can travel, carried by comets, asteroids, and dust, moving from one place to another over long periods of time, like seeds drifting across a landscape, settling wherever they find suitable ground, and over billions of years. This process could create a kind of network where life or its ingredients move between different worlds, linking them together in ways that are slow and subtle, but still meaningful. And when you think about it like that, it changes how we see ourselves, because instead of being completely separate from the rest of the universe, we might be connected to it in a very real way, made from the same materials that exist across space, shaped by processes that are not unique to Earth, but part of a much larger pattern. And while we still have many questions to answer, the idea that life's building blocks are everywhere is a reminder that the story of life is not confined to one planet. It is something that may be woven into the fabric of the universe itself, quietly present in places we have yet to explore, waiting for the right moment to become something more. As the idea of life traveling through space begins to feel more possible, a very natural question rises almost immediately. Even if rocks can move between planets, could anything alive actually survive that journey? Because space is not just empty. It is one of the harshest environments imaginable, far more extreme than any place on Earth, with temperatures so cold they make the deepest winter feel warm, radiation levels strong enough to damage living cells, and a complete lack of air or pressure, like being placed in a vacuum, where even liquids can begin to boil away. So at first, it seems almost impossible that life, even in its simplest form, could endure such conditions. But when scientists started to test this idea, they discovered something surprising, something that slowly changed how we think about life's limits. Because certain microorganisms, especially some types of bacteria, are far more resilient than we once believed, able to survive conditions that would instantly destroy most living things. And this leads to another question: how do we know this? How can we test survival in space without sending everything out there? And the answer comes from a combination of laboratory experiments and real missions, where scientists expose microorganisms to conditions that mimic space, or even place them outside spacecraft for short periods, allowing them to experience the vacuum and radiation directly, and the results have been unexpected. Some of these microorganisms do not just survive, they endure in ways that seem almost unbelievable, like seeds that remain dormant for years, and then suddenly grow when conditions become right again. Except in this case, the dormancy happens in an environment far more extreme than anything those seeds would ever face on Earth. And this resilience is often due to special features within the cells, mechanisms that protect their genetic material and allow them to repair damage once conditions improve, almost like having a built-in repair system that activates when needed. And one example that often surprises people is a type of bacteria known as Deinococcus radiodurans, which can survive radiation levels thousands of times higher than what would be deadly to humans, levels so intense that if a person were exposed to them, it would be like standing next to a powerful source of energy that could cause severe damage in seconds. Yet this microorganism can endure and recover, which makes us pause and ask, if life can survive such extremes here on Earth, what else might it be capable of? And this idea becomes even more interesting when we consider that not all parts of space are equally harsh, because if microorganisms are hidden inside rocks, they can be shielded from much of the radiation and temperature extremes, creating a kind of natural protection, like being inside a thick wall during a storm where the outside conditions are dangerous, but the inside remains relatively stable. And this means that the journey through space might not be as immediately destructive as it first appears, especially for organisms that are already adapted to survive in extreme environments. And this leads to another important question. How long could something survive like this? Because traveling between planets is not instant. It can take thousands or even millions of years, which is like leaving something in a sealed container for a time longer than all of recorded human history. And yet, some microorganisms have shown the ability to remain dormant for very long periods, essentially pausing their activity until conditions become favorable again. And when you combine this with the protection offered by rocks, it creates a scenario where survival, while still difficult, is not entirely impossible. And this idea begins to shift our understanding of life, because it shows that life is not as fragile as we once thought. It is adaptable, resilient, and capable of enduring conditions far beyond what we experience in everyday life. And this naturally supports the idea of panspermia, because if microbes can survive the journey through space, even for limited periods, then the possibility of life traveling between worlds becomes more realistic. Not just a theory, but something that could actually happen under the right conditions. And while we still do not have direct evidence that this has occurred, the experiments and observations we have so far suggest that it is at least possible, and that alone is enough to keep the question open, because science often begins with possibilities that seem unlikely at first, only to become more accepted as evidence grows. And so the idea that microbes can survive space is not just a detail, it is a key piece of the larger puzzle, a piece that helps connect the movement of rocks, the presence of organic molecules, and the early appearance of life on Earth into a story that feels more complete. A story where life is not confined to one place, but capable of moving, enduring, and continuing its journey across the vast distances of space, quietly waiting for the right moment to begin again. As we continue to explore the limits of life, something remarkable begins to stand out, something that quietly changes how we understand what it means for something to be habitable. Because for a long time, people believed that life could only exist in comfortable conditions, places with moderate temperatures, clean water, and a stable environment, something similar to what humans need to survive. But over time, scientists started to discover organisms living in places that seemed completely unfit for life, environments so extreme that they would appear almost alien to us. And these organisms are known as extremophiles, a name that simply means lovers of extreme conditions. And once you begin to look at where they live, it becomes almost unbelievable, because some of them thrive in boiling hot water near hydrothermal vents deep in the ocean, where temperatures can be hot enough to cook food, like placing something in a pot of boiling water on a stove. And yet these organisms not only survive there, they grow and reproduce. Others live in environments that are extremely cold, buried in ice for long periods, where temperatures are far below freezing, colder than any natural winter most people will ever experience. Like being locked inside a freezer that never warms up, and still, they remain alive, slowly carrying out the processes that define life. And this naturally leads to a question: how can anything survive such extremes? Because when we think about heat or cold, we often imagine clear limits, points beyond which survival is impossible. But extremophiles seem to push those limits much further than expected, and they do this through special adaptations, changes in their structure and chemistry that allow them to function where other forms of life would fail, like having tools designed specifically for conditions that would break ordinary ones. And it's not just temperature that they can endure. Some extremophiles live in highly acidic environments, where the surroundings are so corrosive they can dissolve materials over time, similar to how strong cleaning chemicals can damage surfaces if left for too long. While others thrive in highly salty environments, where the concentration of salt is so high that it would draw water out of most cells and cause them to collapse. Yet these organisms have found ways to maintain balance and continue living, And this makes us pause and ask, if life can exist in such extreme places on Earth, could similar life exist in extreme environments elsewhere, perhaps even in space or on other planets? Because what we once thought of as uninhabitable may not be as lifeless as it seems. And this idea becomes even more interesting when we consider that some extremophiles can survive multiple extremes at the same time, enduring both high radiation and extreme dryness, conditions that are closer to those found in space. And this connection is important because it suggests that life does not need perfect conditions to exist. It only needs conditions that it can adapt to. And once it does, it can persist in ways that feel almost surprising. And this challenges another common belief that life is delicate and easily destroyed, because while that may be true for many complex organisms, simpler forms of life can be incredibly tough, capable of enduring situations that would seem impossible at first glance. And this leads to another question: could extremophiles be similar to the kinds of organisms that might travel through space? Because if anything were to survive such a journey, it would likely be something that is already adapted to extreme conditions, something that can handle radiation, lack of water, and large changes in temperature. And when scientists study extremophiles, they begin to see traits that match these requirements, making them strong candidates for what life in space might look like. And this idea helps bridge the gap between what we observe on Earth and what might be possible beyond it, because instead of imagining completely unfamiliar forms of life, we can look at extremophiles as examples of how life adapts and survives, using them as a guide to understand what might happen in other environments. And this also changes how we search for life elsewhere, because instead of only looking for places that resemble Earth closely, we can expand our search to include more extreme environments, places that we might have once ignored, like icy moons with hidden oceans beneath their surfaces, or dry, rocky planets with intense radiation. And while these places may seem hostile, extremophiles remind us that life has a way of finding solutions, adapting to challenges, and continuing even in difficult conditions. And when you think about it, this resilience adds another layer to the idea of panspermia, because if life can survive and thrive in extremes here on Earth, then the possibility of it surviving a journey through space becomes easier to imagine, not as something impossible, but as something that fits within the range of what life is already capable of. And so extremophiles serve as a quiet but powerful example, showing us that life is not limited to gentle environments. It is flexible, adaptable, and far more durable than we once believed, which opens the door to the idea that life could exist in places we have not yet explored, and perhaps even travel between them, continuing its journey across the universe in ways that are slow, subtle, and quietly persistent, like a process that never fully stops, always finding new ways to endure and begin again as we continue to look deeper into the limits of life. One particular challenge stands out as especially difficult to overcome, and that is radiation, an invisible force that carries energy strong enough to damage the very core of living cells, breaking apart the structures that allow life to function. And when we think about space, radiation becomes one of the biggest obstacles for survival, because beyond the protection of Earth's atmosphere, this energy is constant and intense, like standing under a stream of invisible particles that never stops. And over time, that exposure can cause serious harm. So it's natural to wonder, could anything truly survive that kind of environment for long? And the answer, surprisingly, is yes, at least for some forms of life, because certain types of bacteria have shown an ability to withstand levels of radiation that would be instantly fatal to most organisms. And this discovery has changed how scientists think about life's resilience, because it shows that even something as destructive as radiation is not always enough to stop life completely. And one of the most well-known examples of this is a bacterium called Deinococcus radiodurans, which has become almost famous for its incredible ability to survive extreme radiation levels so high that they would be like receiving thousands of medical X-rays all at once, something that would cause severe damage to human cells in a very short time. Yet this bacterium can endure it and recover, which leads to a simple but fascinating question. How does it do that? How can something so small survive something so powerful? And the answer lies in its unique structure and repair systems. Because when radiation damages its DNA, breaking it into pieces, this bacterium has the ability to repair that damage, almost like putting together a puzzle that has been shattered into many parts, carefully reassembling it until it works again. And this process happens with a level of efficiency that is difficult to imagine, allowing the organism to continue living even after what would seem like catastrophic damage. And this ability is not just a minor advantage, it is a powerful example of how life can adapt to extreme conditions over time, developing solutions that allow it to survive where it otherwise could not. And this leads to another important question. If bacteria like this can survive intense radiation on Earth, could similar organisms survive in space, where radiation is constant and unavoidable? And when scientists consider this, the answer becomes more open, because while space is still more extreme overall, the existence of such resilient organisms suggests that survival is at least possible under certain conditions, especially if those organisms are protected in some way, such as being inside rocks or other materials that can block part of the radiation, like standing behind a shield during a storm where the full force is reduced but not completely removed. And this idea ties back to the concept of life traveling through space, because if microorganisms can endure radiation long enough, especially with some level of protection, then the journey between planets becomes more realistic. Not easy, but not impossible either. And this also changes how we think about the boundaries of life. Because instead of seeing radiation as an absolute barrier, something that completely prevents life from existing, we begin to see it as a challenge that some organisms can overcome, at least to a certain extent. And this shifts our perspective, making us realize that life does not always need perfect conditions. It can survive in imperfect ones, adapting to what is available and finding ways to continue. And this idea also connects to the broader question of where life might exist beyond Earth. Because if radiation is not always a complete barrier, then environments that were once considered too harsh might still be capable of supporting life, especially in simple forms. And this opens up new possibilities, suggesting that life could exist in places we have not yet explored, places where radiation levels are high, but not necessarily fatal for all organisms. And as we think about this, it becomes clear that the story of life is not just about fragile beginnings. It is also about resilience, about the ability to endure and recover, even under conditions that seem overwhelming. And bacteria like Deinococcus radiodurans serve as a reminder of that resilience, showing us that life can survive in ways that challenge our expectations. And when we apply that understanding to the idea of panspermia, it becomes easier to imagine how life could travel through space, facing radiation along the way, yet still managing to survive long enough to reach a new environment where it can begin to grow again. And while we still have much to learn, these discoveries help fill in some of the gaps, bringing us closer to understanding how life might move beyond a single planet, quietly continuing its journey across the universe, guided not just by chance, but by an ability to endure that is far greater than we once believed. As we continue to imagine how life might survive the journey through space, one simple but powerful idea begins to stand out. And it is this: what if life does not need to face space directly at all? What if it can travel while hidden, protected inside something solid, something that acts like a natural shield. And this is where rocks begin to play a very important role, because on Earth, scientists have discovered that many microorganisms do not live on the surface where conditions are more exposed, but instead exist deep inside rocks, in tiny cracks and spaces that are invisible to the eye. And this might sound surprising at first, because we often think of rocks as lifeless, solid, and empty, but when examined closely, they can contain small pockets where life can exist, almost like hidden rooms inside a structure. And these spaces provide protection from harsh conditions, shielding the organisms from radiation, extreme temperatures, and sudden changes in the environment. And this naturally leads to a question: how deep can life go inside a rock? And the answer can be quite surprising, because some microorganisms have been found several kilometers below the Earth's surface, which is like going deeper than the height of the tallest mountains, but in the opposite direction, down into the ground, where sunlight never reaches and conditions are very different from the surface. And yet, even there, life continues, slowly carrying out its processes, adapting to the limited resources available. And this shows us something important. Life does not always need light or open space. It can survive in hidden, protected environments. And this idea becomes even more interesting when we think about rocks traveling through space. Because if microorganisms can live inside rocks on Earth, could they also survive inside rocks that are ejected into space? And the answer begins to feel more possible, because the same protection that helps them survive underground could also help them endure the journey beyond our planet, shielding them from radiation and helping to maintain more stable conditions inside, like being inside a thick wall during extreme weather, where the outside environment is dangerous, but the inside remains relatively safe. And this leads to another question: what happens when these rocks enter a planet's atmosphere? Wouldn't the heat destroy anything inside? And while it is true that the outer layers of a meteorite can become extremely hot, often glowing as they pass through the atmosphere, the inside can remain much cooler, because heat takes time to travel inward. And if the rock is large enough, the interior may not heat up enough to harm anything hidden within it, similar to how the inside of a loaf of bread can stay soft, even when the crust becomes hot and firm. And this means that microorganisms deep inside a rock could potentially survive both the journey through space and the final descent onto a planet. And this possibility adds another piece to the larger picture, because it shows that rocks are not just carriers of minerals, they can also act as protective vessels, allowing life to travel without being fully exposed to the harsh conditions outside. And when we think about how many rocks have been exchanged between planets over billions of years, it becomes easier to imagine how this process could happen more than once, like messages being carried back and forth over long distances, slowly and quietly, without anyone noticing. And this idea also changes how we view the boundaries of life, because instead of being limited to open environments, life can exist in hidden places, tucked away inside solid structures, waiting for the right conditions to emerge and grow. And this leads to another thought: if life can survive inside rocks on Earth, and potentially in space, could it also exist inside rocks on other planets? Perhaps even right now, in places we have not yet explored. Because when we search for life beyond Earth, we often look at surfaces, at visible signs. But this perspective suggests that life might be hidden, not immediately obvious, requiring us to look deeper, both literally and figuratively. And this makes the search more challenging, but also more interesting, because it expands the range of places where life might be found. And as we consider all of this, the idea of life hidden inside rocks becomes more than just a possibility. It becomes a key part of understanding how life might move through space, survive extreme conditions, and eventually find a new home, continuing its journey in a way that is slow, subtle, and almost invisible, like something that has been happening quietly for billions of years, shaping the story of life across the universe without drawing attention to itself. And in that quiet process, there may be answers waiting to be discovered, answers that could change how we see not only life on Earth, but life everywhere. When we begin to put all these ideas together, a quiet image starts to form, one that feels both simple and vast at the same time. And that image is this: enormous rocks drifting slowly through space, not just empty and lifeless, but possibly carrying something hidden deep inside, something small, quiet, and alive. And these rocks, known as asteroids, move through space over long periods of time, sometimes taking millions of years to travel from one place to another, like a slow journey that unfolds over a timescale far beyond human experience. And when you imagine this, it naturally leads to a question: could asteroids act as natural vehicles for life, carrying it from one world to another, almost like ships moving across an endless ocean? Except instead of water, they move through the darkness of space, and instead of passengers we can see, they might carry microscopic life hidden within their structure. And this idea becomes more realistic when we consider how asteroids form and move, because many of them are fragments left over from the early formation of the solar system, pieces that never came together to form planets. And over time, they collide, break apart, and sometimes change direction. And during large impacts, pieces of planets can be thrown into space, joining these drifting bodies. And this creates a kind of natural exchange where material from one world becomes part of another object that continues traveling through space. And if that material contains microorganisms hidden inside rocks, then those organisms could be carried along for the journey, protected from the outside environment. And this leads to another question: how long could such a journey take? And the answer is often incredibly long, sometimes millions of years, which is like comparing a single human lifetime to the entire history of life on Earth. It's almost impossible to fully grasp. And yet, as we have seen, some microorganisms can survive in dormant states for very long periods, essentially pausing their activity until conditions become favorable again. And when you combine this ability with the protection offered by rocks, it creates a scenario where survival over long journeys becomes more possible than we might expect. And this idea also connects to something we already know, because scientists have found meteorites on Earth that originated from other planets, including Mars, which means that material can indeed travel between worlds, carried by these natural processes. And this raises a quiet but powerful possibility. If rocks can make that journey, and if life can survive inside rocks, then perhaps life itself has already traveled between planets, not just once, but many times over billions of years, like a slow and steady exchange that has been happening long before humans ever existed. And this changes how we think about the isolation of planets, because instead of being completely separate, they may be connected in subtle ways, sharing material and possibly even life. And this leads to another thought: if life can travel on asteroids within a single solar system, could it also travel between different star systems? And while that idea is much more difficult to imagine because the distances are far greater, it is not entirely impossible, especially when we consider the immense amount of time available in the universe, billions of years during which even very slow processes can have significant effects, like a tiny drop of water slowly shaping a rock over time. And this perspective makes the universe feel more connected, as if life is not confined to one place, but can move, spread, and continue its journey across vast distances, carried by natural processes that do not require intention or direction, but simply follow the laws of physics. And this idea also challenges a common assumption that life must always begin independently on each planet, because if asteroids can carry life from one place to another, then some worlds might not need to start from nothing. They might receive life that has already begun elsewhere, giving it a head start and allowing it to develop more quickly under the right conditions. And this helps explain some of the earlier questions about how life appeared so soon on Earth, because instead of forming entirely from scratch, it may have arrived already partially formed, ready to grow and evolve. And as we think about this, the image of asteroids changes, because instead of seeing them as simple rocks drifting through space, we begin to see them as possible carriers, silent travelers moving through the darkness, holding within them the potential for life. And while we still do not have direct proof that this process has occurred, the pieces of the puzzle are there. The movement of rocks, the resilience of microorganisms, the presence of organic molecules, all coming together to suggest that it is at least possible. And that possibility alone is enough to keep the idea alive, inviting us to look at the universe in a different way, not as a collection of isolated worlds, but as a connected system where life, once it begins, may find ways to continue its journey, moving from one place to another, quietly and persistently, like something that has no clear beginning or end, but simply continues, adapting and evolving as it goes, across distances so vast that they almost feel endless. And within that endless space, asteroids may play a role far greater than we once imagined, not just as remnants of the past, but as carriers of something much more profound, something that could shape the story of life itself across the universe. As we continue following this quiet trail of ideas, one place begins to stand out more than the others, not too far away, not hidden in distant galaxies, but right here in our own solar system, and that place is Mars, a world that today looks cold, dry, and lifeless, covered in dust and rock, with a thin atmosphere and temperatures so low they would feel like standing in a deep freezer that never warms up. But when scientists look closely at Mars, they see signs that it was not always like this. They see evidence that long ago, Mars may have been a very different place, a place with flowing water, rivers, lakes, and possibly even oceans, which raises a simple but powerful question. If Mars once had water and a more stable environment, could it have supported life before Earth did? Because when we think about life, water is one of the most important ingredients, and on early Mars, conditions may have been just right for it to exist on the surface, creating an environment that could support simple forms of life. And this becomes even more interesting when we compare the timelines, because Mars formed around the same time as Earth, but it may have cooled faster, reaching stable conditions earlier, which is like two pots of hot water left to cool, where one becomes comfortable sooner than the other. And if life requires stable conditions to begin, then Mars might have had a head start, giving it more time for life to develop, even if only in simple forms. And this leads to another question. If life did begin on Mars, how could it have reached Earth? And the answer connects back to what we already know about impacts and space travel. Because when large objects collide with a planet, they can send pieces of that planet into space. And some of those pieces can eventually land on other worlds. And we have real evidence of this because scientists have found meteorites on Earth that originated from Mars. Rocks that were once part of its surface, thrown into space by powerful impacts, and later captured by Earth's gravity, which means that material has already made the journey between these two planets. And if that material contained microorganisms hidden inside, protected within the rock, then it is possible that life could have traveled along with it, making the journey from Mars to Earth over long periods of time. And this idea naturally leads to another thought. Could life on Earth actually have Martian origins? Could we, in a very distant sense, be connected to another planet? And while this may sound unusual at first, it is taken seriously by some scientists, because it helps explain some of the puzzles we have been discussing, such as how life appeared relatively quickly on Earth, and how it could have survived the harsh early conditions here. Because if life began on Mars first, in a more stable environment, and then arrived on Earth later, it would not need to start from scratch. Under difficult conditions, it would already exist, ready to adapt and grow. And this idea also shifts how we see Mars itself, because instead of viewing it as a completely separate world, we begin to see it as potentially connected to our own history, a place that may have played a role in the story of life on Earth. And this raises another question. If Mars once supported life, could there still be traces of it today, perhaps hidden beneath the surface, where conditions might still be more stable? And this is one of the reasons why scientists are so interested in exploring Mars, sending rovers and missions to study its surface and search for signs of past or present life, looking for chemical signatures, patterns or structures that might indicate that life once existed there. And while we have not yet found clear evidence of life on Mars, the clues we have are enough to keep the possibility open. And this possibility is important because it connects directly to the idea of panspermia, showing us that life does not need to originate independently on every planet. It can move, spread, and continue its journey, carried by natural processes that link different worlds together. And when you think about it, this makes the solar system feel less like a collection of isolated planets and more like a connected system, where events on one world can influence another, even across the emptiness of space. And this perspective changes how we see ourselves, because instead of being entirely separate, we might be part of a larger story, one that includes not just Earth, but other planets as well. And while we still do not have a final answer, the idea that Mars could have been a source of life for Earth is a powerful reminder that the origins of life may not be as simple as we once believed. They may involve journeys across space, connections between worlds, and a history that extends beyond our own planet, reaching into places that are still waiting to be fully explored, like a story that began somewhere else and continued here, quietly shaping everything we see today. As we continue exploring how life might move from one world to another, one idea becomes clearer and more grounded in real evidence, and that is the simple but powerful fact that rocks do not always stay where they begin. They can travel, sometimes across incredible distances, moving from one planet to another through natural processes that have been happening for billions of years. And at first, this might sound surprising, because we often think of planets as separate and isolated, each one existing on its own. But in reality, there is a quiet exchange that takes place over long periods of time, an exchange driven by powerful impacts that send pieces of one world into space. And when a large asteroid or comet strikes a planet, the energy released can be enormous, strong enough to launch fragments of rock beyond the planet's gravity, like pieces of debris thrown outward from an explosion, except on a much larger scale. And these fragments do not simply disappear. They continue moving through space, following paths shaped by gravity, sometimes drifting for long periods before eventually being pulled toward another planet. And this leads to a natural question: how often does this actually happen? And the answer is more often than we might expect, especially in the early days of the solar system, when impacts were much more common, like a time when objects were colliding, frequently shaping the surfaces of planets and sending material in all directions. And even today, though less frequent, impacts still occur, continuing this slow exchange, and we have clear evidence of this process, because scientists have identified meteorites on Earth that originated from other bodies, including the Moon and Mars, which means that material has successfully traveled across space and landed here. And this is not just a theory, it is something that has already happened. which makes the idea of transfer between planets feel much more real. And this brings us to another important question. What happens to these rocks during their journey? Because space is not a gentle environment. It exposes objects to radiation, extreme temperatures, and long periods of isolation. And yet, as we have seen, rocks can provide protection, especially for anything hidden inside them, creating a kind of natural shield that helps preserve their contents. And this protection becomes crucial when we consider the possibility of life traveling along with these rocks. Because if microorganisms are embedded within the rock, deep enough to be shielded from the worst conditions, then their chances of survival increase. Not guaranteed, but possible. And this leads to another thought. How long would such a journey take? And the answer can vary widely. Sometimes thousands of years, sometimes millions, depending on the path the rock takes and the gravitational forces acting on it. And while that may seem like an impossibly long time, it is important to remember that the universe operates on scales far beyond human experience, where millions of years can pass like moments in a much larger timeline. And some microorganisms have shown the ability to remain dormant for extended periods, essentially pausing their activity until conditions become suitable again, which makes the idea of surviving long journeys more believable. And this creates a picture of a slow but steady process where rocks move between planets, carrying with them whatever is inside, like messages traveling across space without any intention or direction, simply following the paths allowed by physics. And over billions of years, this process could happen many times, creating a kind of connection between different worlds, a subtle link that allows material and possibly life to move from one place to another. And this changes how we think about the solar system, because instead of being a set of isolated environments, it becomes more like a network where events on one planet can influence another, even across great distances. And this leads to another question. If rocks can travel between planets in our solar system, could similar processes happen in other systems as well? And while the distances between stars are much greater, making such transfers more difficult, the basic idea remains the same, that material can move through space under the right conditions, and over long enough timescales, even rare events can occur. And this perspective makes the universe feel more dynamic, more connected, as if it is constantly changing and interacting, even in ways we cannot easily see. And when we think about this in the context of life, it becomes even more meaningful because it suggests that life may not be limited to the place where it begins. It may have the ability to spread, to move, and to continue its journey across different worlds, carried by something as simple as a rock. And while we still do not have direct proof that life has traveled in this way, the evidence of rocks moving between planets provides a strong foundation for the idea, showing that the mechanism exists, that the pathway is real, and that under the right conditions, it could carry more than just minerals. It could carry the beginnings of life itself, quietly crossing the space between worlds, waiting for the right place to begin again. As we continue following this quiet chain of ideas, there comes a moment where the possibility begins to feel less like imagination and more like something grounded in real, physical evidence, because it is one thing to say that rocks can travel between planets, but it is another to actually hold one of those rocks in your hands and know where it came from. And that is exactly what scientists have been able to do, because over time, they have discovered meteorites on Earth that can be traced back to Mars, pieces of another world that made the long journey through space and eventually landed here. And this discovery is not based on guesswork, comes from careful study of the chemical makeup of these rocks, because each planet has its own unique combination of elements and gases, almost like a fingerprint. And by comparing the gases trapped inside these meteorites with the atmosphere of Mars, scientists found a match, showing that these rocks were once part of the Martian surface before being launched into space by powerful impacts. And this leads to a simple but powerful realization. Material from Mars has already reached Earth, which means the pathway between these two planets is not just theoretical, it is real. It has already happened, and likely more than once, over billions of years. And when you think about that, it naturally raises another question. If rocks can make that journey, could anything else have traveled with them? Because if those rocks contained microorganisms hidden inside, protected from the harsh conditions of space, then it is possible that life, or at least the beginnings of it, could have made the same trip. And this idea becomes even more interesting when we consider the number of these meteorites that have been found, because scientists have identified dozens of them, each one telling the same story of a journey that began on Mars and ended on Earth, like messages sent across space over long periods of time. And while most of these rocks show no direct evidence of life, their existence alone is enough to keep the question open, because they demonstrate that the transfer of material between planets is not rare or unusual. It is part of the natural history of our solar system. And this leads to another thought. How long did these rocks travel before reaching Earth? And the answer can vary. Some may have taken only a few thousand years, while others could have spent millions of years drifting through space, which is like comparing a short trip to one that lasts longer than the entire history of human civilization. And yet, as we have seen, some microorganisms are capable of surviving long periods in dormant states, especially if they are protected within rock, which makes the idea of survival over such timescales more believable. And this connection between real meteorites and the possibility of life traveling with them is what makes this part of the story so compelling, because it brings together observation and imagination, showing that the conditions needed for panspermia are not purely hypothetical. They exist, they have been observed, and they continue to occur. And this also changes how we think about the relationship between Earth and Mars, because instead of being completely separate worlds, they may have been connected through these exchanges of material, sharing pieces of themselves over time. And this raises another quiet question. If life did exist on Mars in the past, could some of it have survived the journey to Earth and continued its existence here, becoming part of the life we see today? And while we do not yet have evidence to confirm this, it remains a possibility that scientists take seriously, because it offers a way to explain some of the earlier questions about how life appeared relatively quickly on Earth and how it could have survived the harsh conditions of the early environment. And as we think about this, it becomes clear that these Martian meteorites are more than just rocks. They are clues, pieces of a larger puzzle that help us understand how the solar system works, how planets interact, and how life might move between them. And this perspective makes the universe feel less isolated, less divided, as if there are connections that we are only beginning to notice, connections that have been there all along, quietly shaping the history of our planet, and possibly others. And when you hold one of these meteorites, you are not just holding a rock, you are holding a piece of another world, a fragment of a journey that crossed millions of kilometers of space, which is like traveling around the Earth thousands of times over. And that journey reminds us that the boundaries we imagine between planets are not as absolute as they seem, because over time, material can move, connections can form, and within those connections, there may be a story of life that extends beyond a single world, a story that continues to unfold slowly and quietly across the vast distances of space. As we continue expanding this idea, it slowly begins to stretch beyond our own solar system, reaching into distances that are almost impossible to fully imagine. And this is where the concept becomes even more fascinating, because until now, we have been thinking about life moving between nearby planets, like Earth and Mars. But what if the journey does not stop there? What if life can travel not just between planets, but between entire star systems, crossing the vast spaces that separate one sun from another? And this idea is known as interstellar panspermia. And at first, it might sound too extreme, too distant to be realistic, because the distances between stars are enormous, far greater than anything within our solar system, for example. The nearest star system to us is more than 4 light years away, which means that even light, traveling faster than anything we know, takes over 4 years to reach it. And if you tried to travel that same distance at the speed of a modern spacecraft, it would take tens of thousands of years, which is like comparing a single human lifetime to a span of time that stretches far beyond recorded history. So this naturally leads to a question. How could anything survive such a journey? How could life endure not just years, but thousands or even millions of years in the harsh environment of space? And this is where the idea becomes challenging, because while we have seen that microorganisms can survive extreme conditions for limited periods, the timescales involved in interstellar travel are much longer. And yet, when scientists consider the age of the universe, which is over 13 billion years, it opens up a different perspective. Because with so much time available, even very slow processes can have meaningful effects, like a tiny stream of water slowly shaping a landscape over thousands of years. Something that seems insignificant in the short term but becomes powerful over long periods. And this leads to another thought. What if life does not need to travel quickly? What if it can move slowly, carried by objects that drift through space over vast stretches of time? And there are objects that could make such journeys, including comets and fragments of planetary material that are ejected from star systems during powerful events. And once they leave the gravitational pull of their original system, they can drift through interstellar space, like travelers moving between distant islands, guided only by the forces of gravity and motion. And over millions or billions of years, some of these objects could eventually be captured by another star system, bringing with them whatever they carry. And this includes the possibility of microorganisms hidden within rocks, protected from some of the harsh conditions outside. And while the chances of any single object making such a journey and successfully delivering life might be very small, the sheer number of stars and the immense amount of time available make the overall possibility more realistic. Because when you multiply small chances by enormous numbers, the outcome can become significant, like buying a single lottery ticket with very low odds compared to buying millions of tickets over a long period. Eventually, the unlikely becomes possible, and this perspective changes how we think about the spread of life. Because instead of being confined to one solar system, life could potentially move between them, creating a kind of slow, cosmic exchange that connects distant parts of the galaxy. And this leads to another question. If life can spread in this way, could it mean that life in different parts of the universe shares a common origin? Could there be a distant connection between life forms that exist on planets, separated by vast distances? And while we do not yet have evidence to confirm this, it is an idea that scientists consider because it offers a way to explain how life could appear in multiple places without needing to start from scratch each time. And this also challenges a common assumption that life must arise independently on every planet where it exists. Because if interstellar panspermia is possible, then some of those instances of life might actually be connected, part of a larger chain that stretches across space and time. And as we think about this, the universe begins to feel less like a collection of isolated systems and more like a connected whole, where material and possibly life can move between stars, slowly but steadily, guided by natural processes that operate over immense timescales, and while this idea remains difficult to test and prove, it is supported by the same principles we have already explored: the movement of rocks, the resilience of microorganisms, and the presence of organic molecules in space, all of which suggest that the ingredients and mechanisms needed for such a process exist, and this makes interstellar panspermia not just a distant speculation, but a possibility that invites us to look at the universe in a new way, as a place where life, once it begins, may not remain confined to its original home, but could continue its journey across the stars, carried by objects that drift through the darkness, slowly bridging the gaps between worlds, and in doing so, creating connections that span distances so vast they are almost beyond comprehension, like a story that is written not in years or centuries, but in millions and billions of years, unfolding quietly across the endless expanse of space. As we continue exploring how life might travel across space, another type of object begins to come into focus, one that is often seen as beautiful and mysterious when it passes through the night sky, leaving behind a glowing trail that stretches across the darkness. And that object is a comet. And while comets may look like simple streaks of light from a distance, they are actually large, icy bodies made of frozen water, dust, and organic compounds, almost like ancient time capsules that have remained mostly unchanged since the early formation of the solar system. And when scientists study comets more closely, they discover something very interesting, because these objects contain many of the same building blocks associated with life, including complex carbon-based molecules. And this leads to a natural question: could comets have played a role in bringing life, or at least its ingredients, to Earth? Because unlike solid rocks, comets are rich in ice, and that ice can contain trapped molecules that formed in space long before planets like Earth existed. And when comets travel through the inner parts of a solar system and approach a star, the heat causes some of that ice to vaporize, releasing gas and dust into space, creating the glowing tail that we see. And in that process, materials from the comet are spread out like fine particles drifting away from a source. And sometimes, fragments of comets can break off or collide with planets, delivering their contents directly to the surface. And this idea becomes even more interesting when we think about early Earth, because during its formation, our planet was bombarded by many objects, including comets, and some scientists believe that comets may have contributed not only organic molecules, but also a significant amount of water, helping to fill the early oceans, which is like slowly pouring water into a dry basin until it becomes a vast sea. And if that is the case, then comets may have played a role in creating the conditions necessary for life to exist, as well as providing some of the ingredients needed for it to begin. And this leads to another question: could comets also carry microorganisms, not just molecules? And while this idea is more difficult to confirm, it connects to what we have already discussed about life surviving in extreme conditions. Because if microorganisms can survive inside rocks, protected from radiation and temperature changes, then it is possible that similar protection could exist within the icy interior of a comet, where conditions might remain stable enough to allow survival over long periods, almost like being frozen in time, preserved until the right conditions allow activity to resume. And this idea becomes even more fascinating when we consider how long comets can travel, because some of them originate from distant regions of the solar system, such as the Oort cloud, a vast area far beyond the orbit of the planets, where icy objects can remain for billions of years. And when one of these comets is disturbed and begins moving toward the inner solar system, it carries with it materials that have been preserved since the earliest days of planetary formation, which is like opening a container that has been sealed for an incredibly long time, revealing what was inside from the very beginning. And this connection between comets and the early history of the solar system makes them important objects of study because they provide clues about what was present when planets like Earth were forming. And this leads to another thought. If comets can deliver organic molecules and possibly even microorganisms, could they have been part of a larger process that helped spread life across different worlds, acting as carriers that move materials from one place to another? And while we do not yet have direct evidence that living organisms have been delivered by comets, the presence of complex molecules within them shows that they at least carry the ingredients needed for life. And that alone is significant because it suggests that space is not empty of life-related material, but filled with it, and comets may be one of the ways that this material is transported, slowly and steadily across different regions. And when you think about it, this changes how we see these glowing objects in the sky, because instead of being just beautiful sights, they become part of a much larger story, one that involves the movement of matter, the formation of planets, and the possible spread of life itself. And this perspective makes the universe feel more active, more connected, as if there are processes happening quietly over long periods that link different places together. And within those processes, comets may play a role that is both simple and profound, acting as carriers of the materials that make life possible, moving through space in slow, graceful paths, and occasionally bringing their contents to new worlds, where those materials can take part in the ongoing story of life, a story that may not begin or end in one place, but continues across space and time, shaped by the movement of objects like comets that travel through the darkness, carrying with them the potential for something extraordinary to begin again. As all these pieces slowly come together, a quiet but powerful idea begins to emerge, one that feels both simple and deeply profound at the same time. And that idea is this: what if life is not something rare and isolated? What if it is not something that happened only once on one small planet, but instead something that exists throughout the universe, appearing wherever the right conditions are met, almost like a pattern that repeats itself again and again across different places? And when you think about everything we have explored so far, this idea starts to feel less distant and more natural, because we have seen that the building blocks of life are found everywhere, scattered across space in meteorites, comets, and clouds between stars. And we have seen that life on Earth can survive in extreme conditions, adapting to environments that once seemed impossible. And we have also seen that material can travel between planets, and possibly even between star systems, carrying with it the ingredients needed for life. And all of this leads to a simple question: if all the necessary pieces are so widespread, why would life exist in only one place? Why would the universe create the same conditions again and again, but produce life only once? And this question challenges a common belief, because many people grow up thinking that life on Earth is unique, something special that happened here and nowhere else. But when we look at the evidence, that idea becomes less certain, because the more we learn about the universe, the more we see that it follows patterns, that the same physical laws apply everywhere, that stars form in similar ways, planets form from the same kinds of materials, and chemical reactions occur under similar conditions. And if all of that is consistent, then it becomes reasonable to think that life, which is based on those same physical and chemical processes, might also follow a similar pattern, appearing wherever those conditions come together in the right way. And this leads to another thought: what would it mean if life is truly universal? If it exists, not just here, but across many worlds, in different forms and environments? Because it would change how we see ourselves. It would mean that we are not alone in the sense of being the only example of life, but part of a much larger system, a universe where life is woven into its structure, quietly present in places we have yet to explore. And this idea can feel both exciting and humbling at the same time, Because on one hand, it suggests that life is common, that it may exist in countless places, each with its own story, its own path of development. And on the other hand, it reminds us that we are just one small part of something much bigger, like a single drop of water in a vast ocean. And this naturally leads to another question. If life is universal, why haven't we found clear evidence of it yet? Why does space still seem so quiet? And the answer may be that the universe is simply very large, far larger than we can easily explore. And even if life is common, it may be spread out over distances so great that finding it takes time, effort, and the right tools. And we are still in the early stages of that search, like someone standing at the edge of a forest and only seeing the first few trees, not yet aware of how far it extends. And it is also possible that much of life in the universe exists in simple forms, microscopic and difficult to detect, not producing obvious signals or structures that we can easily observe from a distance, which makes the search even more challenging, but not impossible. And as we continue to develop new technologies and explore more of our solar system and beyond, we may begin to find signs that support this idea, small clues that suggest life is not confined to Earth, but part of a much larger pattern. And when you think about this, the idea of panspermia fits naturally into this picture, because if life is universal, then the spreading of life from one place to another becomes a way of connecting different worlds, allowing life to move, adapt, and continue its journey across space. And this creates a vision of the universe that is not empty and silent, but quietly alive, filled with processes that support the emergence and continuation of life. And while we may not yet have all the answers, the idea that life is universal invites us to look at the cosmos in a different way, not as a vast emptiness, but as a place full of potential, where life may exist in forms we have not yet imagined, waiting to be discovered. And in that possibility, there is a sense of connection, a reminder that the story of life may not begin and end with us, but may be part of something much larger, something that stretches across space and time, unfolding quietly in ways that we are only beginning to understand, like a pattern that repeats itself across the universe, linking distant worlds together through the simple but profound presence of life. As this idea continues to unfold, it gently leads us to one of the most personal and thought-provoking questions of all, a question that feels almost unreal at first, yet follows naturally from everything we have explored so far. If life can travel through space, if it can survive inside rocks, if it can move between planets and possibly even between stars, then what does that say about us? About where we come from? Because when we look at ourselves, it is easy to think of life on Earth as something that began here and developed independently. But if panspermia is true, even in its simplest form, then there is another possibility, a quiet and fascinating one, that the earliest forms of life on Earth may not have originated here at all, but instead arrived from somewhere else, carried across space long before humans, animals, or even plants existed. And this leads to a simple but powerful question. Could we, in a very distant sense, be descendants of life that came from beyond Earth? And while this might sound like something from a story, it is actually a serious idea that scientists consider, not in the sense of advanced alien beings arriving and creating life directly, but in the much simpler sense of microscopic organisms, tiny and basic forms of life, making their way here and becoming the starting point for everything that followed. And this distinction is important because many people imagine the idea of alien origins in dramatic ways, but the reality, if it is true, would be far quieter and more subtle, involving life so small that it would be invisible without a microscope, yet capable of growing, evolving, and eventually leading to the incredible diversity of life we see today. And this naturally leads to another question: how different would that make us if our origins are not entirely Earth-based? And the answer may be both simple and surprising, because even if life began elsewhere, it has spent billions of years evolving on Earth, shaped by this planet's environment, its oceans, its atmosphere, and its unique history, which means that while the starting point might be different, the path that followed is still deeply connected to Earth. Like a tree that was planted from a seed, carried by the wind, it may not have started in that exact spot, but everything it becomes is shaped by where it grows. And this perspective helps us understand that the idea of extraterrestrial origins does not make life here any less connected to this planet. It simply adds another layer to the story, a deeper beginning that reaches beyond what we can see. And this leads to another thought. If life on Earth shares a common origin with life elsewhere, does that mean we are connected to other forms of life in the universe, even if we have never encountered them? And while we do not yet have evidence of such life, the idea itself creates a sense of connection, suggesting that life, wherever it exists, may share certain fundamental traits, built from the same kinds of molecules, following similar processes, because the laws of chemistry and physics are the same everywhere. And this makes it more likely that life, even in different places, might not be completely unfamiliar, but instead share a common foundation. And this idea also challenges a common belief that life on Earth is entirely separate from the rest of the universe. Because if Panspermia is true, then our story is not isolated. It is part of a larger process, one that involves movement, exchange, and continuity across space. And this shifts how we see ourselves, because instead of being the center of the story, we become part of it, participants in a much larger narrative that extends beyond our planet. And this perspective can feel both humbling and fascinating, because it reminds us that the origins of life may be more complex than we once thought, involving not just one place and one moment, but a series of events that span vast distances and long periods of time. And as we think about this, the idea of being descendants of alien microbes becomes less about something strange or unfamiliar, and more about understanding the continuity of life, how it can move, adapt, and continue its journey across different environments. And this leads to another quiet question. If life has traveled to Earth in the past, could it still be arriving even now, carried by meteorites and dust, continuing the same process that may have started billions of years ago? And while we do not have clear evidence of this happening today, the possibility remains, because the processes that allow material to move between worlds are still active, and over time, they continue to shape the history of our planet. And in that ongoing process, there may be connections that we are only beginning to understand. Connections that link us not just to Earth, but to the wider universe. And when you think about it, this idea changes the way we see life itself, not as something that belongs to one place, but as something that can travel, spread, and continue, like a story that does not begin or end in one location, but moves across space and time, carried by the simplest forms of life, quietly shaping the universe in ways that are both subtle and profound. And within that story, we are not separate observers, but part of the journey, part of a process that may have started far beyond our planet and continues even now, unfolding in ways we are only beginning to understand. As this idea continues to grow and connect more pieces together, a quiet but very important question naturally rises, one that many people wonder about almost immediately. If life can travel through space, if the building blocks are everywhere, and if the conditions seem possible, then why haven't we found direct proof yet? Why don't we have clear, undeniable evidence that life came from space, something we can point to and say with certainty, this is it? And this question is not just reasonable, it is essential, because in science, because in science, ideas are not accepted simply because they are interesting or possible. They need evidence, something that can be observed, tested, and confirmed. And when it comes to panspermia, that kind of proof is extremely difficult to find. And this leads to another question. What would count as proof? What kind of evidence would we need to show that life came from beyond Earth? And the answer is not simple, because we would need to find something that clearly shows life existed elsewhere and then made its way here, something like microorganisms inside a meteorite that can be proven to be truly extraterrestrial, not contaminated by Earth after landing. And that is where one of the biggest challenges appears, because once a meteorite lands on Earth, it is immediately exposed to our environment, to air, water, and countless microorganisms, and distinguishing between what was originally inside the rock and what may have entered later becomes very difficult, like trying to determine whether a drop of water in a cup came from the rain or was added afterward. Once everything is mixed together, it is not easy to trace it back, and this has led to moments of excitement followed by careful reconsideration, because there have been times when scientists believed they had found signs of life in meteorites, only to later question those findings, realizing that the evidence was not as clear as it first seemed. And this highlights another important point. Science moves carefully. It requires strong evidence and repeated confirmation, not just a single observation. And this is why the question remains open, not because there is no possibility, but because the level of proof required is very high. And this leads to another thought. Could it be that we simply have not looked in the right places yet, or that our tools are not advanced enough to detect what we are searching for? Because when we consider the scale of space, it becomes clear that our exploration is still very limited. We have only studied a small number of meteorites in detail, sent a few missions to nearby planets, and begun to analyze samples from space. But compared to the vastness of the universe, this is like examining a handful of grains from an entire beach and trying to understand the whole shoreline. And this perspective suggests that the absence of proof does not necessarily mean the absence of truth. It may simply mean that we are still early in the process of discovery. And this idea is important because many scientific discoveries begin with possibilities that are not immediately proven, ideas that take time, new technology, and further exploration before they can be confirmed. And this leads to another question. What kind of discoveries could change this? What could provide the evidence we are looking for? And there are several possibilities, such as finding clear signs of past or present life on other planets, like Mars, or detecting microorganisms in samples collected from asteroids or comets that show characteristics unlike anything found on Earth, or even discovering life in environments beyond our planet that share similarities with life here, suggesting a common origin. And each of these possibilities represents a step forward, a way of gathering more information that could eventually lead to a clearer answer. And this process takes time, patience, and careful study, because the questions we are asking are not simple. They involve events that may have happened billions of years ago, under conditions that are difficult to recreate or observe directly. And as we think about this, it becomes clear that the lack of direct proof is not a failure, but part of the journey, part of the process of understanding something that is both complex and far-reaching. And this perspective helps us remain open to new ideas, while also staying grounded in evidence, allowing us to explore possibilities without accepting them too quickly. And in this balance, the idea of panspermia continues to exist, not as a confirmed answer, but as a meaningful question, one that invites further exploration and deeper understanding. And while we may not yet have the final proof, the clues we have gathered so far are enough to keep us looking, to keep us asking, and to keep us moving forward. slowly uncovering the story of life and its origins, a story that may be more connected to the universe than we once believed. And as we continue this search, each discovery, no matter how small, brings us a little closer to understanding whether life truly began here or whether it arrived from somewhere far beyond, carried across space in ways we are only beginning to understand, like a mystery that unfolds piece by piece, revealing itself over time as we learn to see the universe with clearer eyes and a deeper sense of curiosity. As we continue to follow this quiet thread of ideas, another possibility begins to appear, one that feels both subtle and surprisingly powerful, and that is the thought that life on Earth may not have started just once, but possibly many times in different places, under different conditions, across long stretches of time. And this idea naturally leads to a question: what if the origin of life is not a single event, but a repeated process, something that can happen again and again when the conditions are right? Because when we look at early Earth, we see a planet that was constantly changing, with environments forming, shifting, and sometimes disappearing, like a landscape that is always being reshaped. And within that landscape, there may have been many opportunities for life to begin. Not just one moment, but multiple moments. Each one like a small spark that has the potential to grow, and some of those sparks may have faded, unable to survive the harsh conditions, while others may have continued, eventually leading to the life we see today. And this leads to another question: how would we know if life started more than once? Because when we study life on Earth, we find that all living things share a common structure at the most basic level, using the same genetic code, the same fundamental processes, which suggests that all life as we know it today came from a single common ancestor, like branches of a tree that all connect back to one root. But this does not necessarily mean that there were no other beginnings. It simply means that if there were, they did not survive, or did not leave descendants that we can observe today. And this idea becomes even more interesting when we combine it with panspermia. Because if life can arrive from space, then it is possible that Earth received life more than once from different sources at different times, like seeds carried by the wind that land in different places, some taking root and growing, others disappearing without a trace. And this raises another quiet question: could there have been multiple forms of early life on Earth, competing, interacting, or simply existing side by side before one form became dominant? And while we do not have clear evidence of this, it is a possibility that scientists consider, because early Earth was a complex and dynamic environment, and it may have allowed for more than one pathway to life, at least for a time. And this idea also helps explain why life appears relatively quickly in the geological record, because instead of relying on a single rare event, it could be the result of multiple attempts, increasing the chances that at least one would succeed, like trying to light a fire in different places until one finally catches and continues to burn. And this perspective changes how we think about the origin of life, because it suggests that the process may not be as fragile or unlikely as it sometimes seems. It may be something that can happen under the right conditions more than once, given enough time and opportunity. And this leads to another thought: if life can start multiple times on one planet, could it also start independently on different planets across the universe, even without panspermia, creating separate origins that later connect or remain independent? And this possibility adds another layer to the idea that life may be widespread, because it suggests that the universe does not rely on a single starting point, but may have many, each one contributing to the overall presence of life. And when you think about this, it creates a picture of the universe that is rich with potential, where life can begin, spread, and evolve in different ways, sometimes connected, sometimes separate, but all part of a larger pattern. And this also brings us back to a common misunderstanding. because many people think of the origin of life as a single, clear moment, like flipping a switch from non-living to living. But in reality, it may have been a gradual process with many steps and many attempts, some successful, others not, and this gradual view makes the idea of multiple beginnings more natural because it allows for variation for different pathways and for outcomes that are shaped by the conditions present at the time. And as we reflect on this, it becomes clear that the story of life may be more complex than a single origin. It may involve layers of beginnings, some on Earth, some possibly beyond it, each contributing in different ways. And while we may never know exactly how many times life began or how many attempts were made, the possibility itself invites us to think more broadly, to see life not as a single event, but as a process, something that can emerge, disappear, and emerge again, shaped by the environment and the opportunities available. And in that process, there is a sense of continuity, a sense that life, once possible, may find ways to begin again, whether on Earth or elsewhere, quietly repeating the same basic steps under different conditions, like a pattern that appears in different places, each time slightly different, yet connected by the same underlying principles. And within that pattern, our own existence becomes part of a much larger story, one that may include many beginnings, many paths, and many possibilities, all unfolding across time and space, in ways that we are only beginning to understand. As we gently step back and look at everything we have explored so far, a quiet realization begins to take shape, one that feels both exciting and deeply thought-provoking, because if life can begin more than once, if its building blocks are spread across space, and if it can travel between worlds, then what does that mean for life beyond Earth? What does it suggest about the possibility of alien life? And this leads to a simple but powerful question. If all the pieces are already there, how likely is it that life exists elsewhere right now, not just in the past, but at this very moment, somewhere out there in the vastness of the universe? And when we think about the scale of that universe, it becomes easier to imagine, because there are billions of galaxies, each containing billions of stars, and around many of those stars are planets, which means there are more potential homes for life than we can easily picture. It is like trying to count every drop of water in all the oceans on Earth, and realizing that you would still not come close to the true number. And with so many possibilities, it begins to feel less like a question of if life exists elsewhere, and more like a question of where and in what form. And this naturally leads to another thought. What might that life look like? Would it be similar to life on Earth, or completely different? And while it is easy to imagine strange and unfamiliar forms, the basic principles of chemistry suggest that some aspects of life might be similar, because the same elements, like carbon, hydrogen, and oxygen, are found throughout the universe, and they tend to behave in consistent ways, forming molecules that can interact and build complexity, which means that even if alien life looks different on the surface, it might still share a common foundation with life here, built from the same kinds of building blocks, following similar processes. And this idea becomes even more interesting when we consider panspermia, because if life can travel between worlds, then some forms of life in different places might actually be related, sharing a distant connection, like branches of a tree that have grown far apart but still trace back to the same root. And this raises another question. If life is widespread, why does space still seem so quiet? Why haven't we clearly detected it yet? And this brings us back to the challenges of observation, because the universe is incredibly vast. And even if life exists in many places, it may be separated by distances so large that communication or detection becomes very difficult, like trying to hear a whisper from across an entire ocean. And it is also possible that much of the life out there is simple, microscopic, and not producing signals that we can easily detect, which means that it could exist without us noticing, hidden in environments we have not yet explored or observed closely enough. And this idea encourages us to expand our search, to look not just for advanced civilizations, but for any signs of life, even in its simplest forms, because those forms may be far more common. And this leads to another thought: how would discovering alien life change our understanding of ourselves? And the answer is both simple and profound, because it would show us that life is not unique to Earth, that it is part of a larger pattern that extends beyond our planet. And this could shift our perspective, helping us see ourselves not as isolated, but as connected to a wider universe, part of a shared process that unfolds across many worlds. And this perspective can be both humbling and inspiring, because it reminds us that we are not the only example of life, yet we are still a unique expression of it, shaped by our own environment and history. And as we think about this, it becomes clear that the implications of panspermia and the widespread nature of life go far beyond science. They touch on how we see our place in the universe, how we understand our origins, and how we relate to the possibility of life beyond Earth. And this leads to one final question in this part of the journey. Are we ready to find life elsewhere? Are we prepared for what that discovery might mean? And while we cannot fully predict how such a discovery would affect us, we can say that it would deepen our understanding, expand our view of the universe, and perhaps bring a new sense of connection, showing us that life is not confined to one place, but is part of something much larger, something that continues to unfold across space and time, quietly and steadily, waiting for us to discover it, like a vast story that we have only just begun to read, one that stretches far beyond our own world and invites us to keep exploring, keep questioning, and keep wondering about what else might be out there, beyond the boundaries of what we currently know. As we slowly reach the edge of this long and quiet journey, one final idea begins to settle in, not loud or dramatic, but calm and deeply unsettling in its own way. Because after everything we have explored, after thinking about life traveling through space, surviving inside rocks, moving between planets, and possibly even between stars, there is one possibility that gently rises above the rest. And it is this: what if life does not belong to Earth at all? What if it never truly began here, but is instead part of something much larger? Something that moves through the universe in ways we are only beginning to understand. And this leads to a simple but powerful question. What if we are not the origin, but a continuation? Just one step in a chain that stretches far beyond our planet. And when you think about this, it changes how everything feels, because it suggests that life is not rooted in one place, but is something that spreads, something that travels, something that continues, like a quiet wave moving across an endless ocean, reaching new shores over time. And this idea can feel both fascinating and slightly unsettling at the same time, because it challenges a deep assumption, the idea that Earth is the starting point, the place where everything began. But if life came from somewhere else, then our story is not the beginning. It is part of a much larger story, one that may have started long before Earth even formed. And this leads to another thought. If life can spread in this way, could it be happening everywhere, across countless worlds, quietly moving from one place to another, carried by rocks, comets, and dust, like seeds drifting through the wind? And over billions of years, this process could create a vast network where life is not isolated, but connected, where different worlds share pieces of the same origin, even if they never directly interact. And this creates a picture of the universe that is very different from what we often imagine, because instead of being mostly empty with rare pockets of life, it becomes something more active, more connected, a place where life, once it begins, does not stay still. It moves, It adapts, it continues, and this leads to another quiet question. If life spreads like this, where did it truly begin? Because even if it did not start on Earth, it must have started somewhere, and that question takes us even deeper, beyond our solar system, beyond nearby stars, into a level of mystery that we may not yet be able to fully answer. And this is where the idea becomes both beautiful and unsettling, because it suggests that the origin of life may be something far beyond our current understanding, something that happened under conditions we have not yet observed, or perhaps something that has happened many times, in many places, creating multiple starting points that eventually connect. And this uncertainty is part of what makes the idea feel so powerful, because it reminds us that there are still things we do not know, still questions that remain open, even as we learn more about the universe. And this leads to another thought. Does this make life feel less special if it is not unique to Earth? And the answer is not as simple as it might seem, because even if life is widespread, each instance of it is still unique, shaped by its environment, its history, and the path it takes over time, like two trees growing from the same type of seed in different places, each one developing in its own way. And so life on Earth remains special, not because it is the only example, but because it is our example, the one we experience and understand. And this perspective allows us to see both the uniqueness and the connection at the same time, to appreciate our place in the universe, while also recognizing that we may be part of something much larger. And as we sit with this idea, it begins to feel less like something to fear and more like something to understand. Because even if life does not belong solely to Earth, it still belongs to us, in the sense that we are part of it, part of its ongoing journey. And this journey may not have a clear beginning or end. It may simply continue, moving across space and time, adapting, evolving, and finding new places to exist. And in that continuity, there is a sense of quiet wonder, a reminder that the universe is not just a place of empty space and distant stars, but a place where life may be present in ways we are only beginning to see. And as this thought settles in, it leaves us with one final question, one that lingers gently in the background. If life is part of a much larger chain, spreading silently across the universe, then where will it go next? And what role will we play in that journey? Because whether we realize it or not, we are already part of it, part of a story that extends far beyond our planet, a story that continues to unfold quietly and endlessly across the vast and open expanse of space.